Good morning, students. Today, we are having lesson 4 of the chapter Electromagnetic Induction and Alternating Currents. We have previously seen in this chapter what is electromagnetic induction. We have also seen the series of experiments conducted by Michael Faraday while discovering electromagnetic induction. And we have learned the laws put forward by Michael Faraday, the first and second law of electromagnetic induction, and also Lenz's law, which gives us the direction of the EMF developed during this process. Now, today we are going to see deeper into what happens within the coil during electromagnetic induction, and we will be learning two new concepts called self-induction and mutual induction. And we will also see how we apply this idea of mutual induction to develop transformers, which are widely used now in order to transfer electric current generated at one place to different parts of the world. So let us go into the topic and see what is self-induction and mutual induction. So you know that when current is flowing through a coil of wire, a magnetic field is developed. So here you can see a simple circuit consisting of a cell, a switch, and a coil of wire wound in the form of a helix. Now, when you switch on, okay, let us go slowly. When we switch on, what will happen? The current will flow into the coil from the cell, right? So initially, when the switch was off, the current through this coil was zero and there was no magnetic flux through the coil. So suppose the magnetic flux initially was 0 Webers. Now when we switch on, what happens? The current slowly increases, say up to 3 amperes. So the current increases from 3 amperes from 0 ampere to 3 ampere. And at that time, what happens? The flux, magnetic flux, also will increase from 0 to some value, say 6 Webers. Suppose it's an exaggeration still. Let us assume that the Weber or the magnetic flux increases from 0 to 6 Webers. So what happens? The magnetic flux linked with this coil of wire is changing. So when the magnetic flux linked with the coil of wire changes, what happens? By Michael Faraday's law of electromagnetic induction, an EMF is developed. So a EMF is developed in this coil of wire due to the change of magnetic flux linked with this coil. And the EMF developed, according to Lenz's law, will try to oppose the change in current. We know that the current is increasing in this direction. The current is flowing in this direction. So the newly developed EMF will be such that it will try to oppose the current, or the induced EMF will make the current flow in the opposite direction. This is called self-induction because here electromagnetic induction happens due to the change in current and resulting change in magnetic flux of the coil itself. So let us see what is self-induction. The magnetic flux linked with the coil changes if the current in the coil changes, as we saw here. The electromagnetic induction due to this is called self-induction. So here you can see a figure, again with a battery, a switch, and a coil of wire, in which The current I is flowing in this direction when the switch is on. As we saw before, as the current flows, a magnetic flux is developed in between this coil. So the magnetic flux increases from 0 to a particular value when the current increases from 0 to I amperes. So during that time, what happens? There is a change in magnetic flux. So there will be electromagnetic induction and a EMF is induced in this coil of wire. As you can see here, the induced EMF will be in a direction that opposes the current. So it will make the current flow in the opposite direction, or it will oppose the increase in current. So let us see mathematically how we can explain it. If phi is the magnetic flux developed in the coil due to the current I, then phi is directly proportional to I, because more current we apply, more will be the magnetic flux. So phi is directly proportional to I, or phi is equal to a constant L into I. This constant of proportionality is called self-inductance. It is denoted by the letter L. So L represents coefficient of self-induction, or it is called self-inductance. So here from this equation, phi is equal to Li, we can define self-inductance. Suppose the current I is 1 ampere. Then what will be L? Phi. So L will be equal to phi. So from this we can define self-inductance as the magnetic flux linked with the coil when unit current flows through it. So what is self-inductance? It is the magnetic flux linked with the coil when unit current flows through it. Now, another definition of self-inductance is also possible. You know that by Michael Faraday's law of electromagnetic induction, we have the EMF induced in a coil due to change in magnetic flux. E or epsilon is equal to minus d phi by dt. This minus is the contribution of Lenz's law. So EMF is equal to minus d phi by dt, or EMF is equal to minus, instead of phi, I'm substituting Li. So minus dLi by dt. L we know is a constant. It's a constant of proportionality. It may depend upon the size of the coil. So it will be depending on the area of cross section of the coil and all. But for a given coil, L will be constant. So we can take L out from this differentiation because it is not dependent on time. So EMF is equal to minus L into di by dt. And what is di by dt? It's the rate of change of current. What if rate of change of current di by dt is equal to 1? Then the self-inductance, its magnitude will be equal to the magnitude of the EMF. I'm talking about the magnitude, neglecting the negative sign. So here, if di by dt is equal to 1, then the self-inductance will be equal to the magnitude of EMF. So we get the second definition for self-inductance. That is, self-inductance is the EMF induced in the coil if the rate of change of current is unity. So we got two definitions for self-inductance. One is that it is the magnetic flux linked with the coil when unit current flows through it. That comes from the equation phi is equal to Li, where phi is the magnetic flux produced in the coil of wire due to a current I. And another definition of self-inductance is that It is the EMF induced in the coil if the rate of change of current is unity. We get this expression from this definition from this expression. EMF is equal to minus L di by dt. Now, if there are n number of turns in the coil, then the equation will become EMF is equal to minus NL di by dt. And I want you to memorize these two equations. Phi is equal to Li and EMF is equal to minus NL di by dt. So here n is the number of turns and di by dt is the rate of change of current. Or if you know the initial current and the final current, you can take it as the final current minus initial current, the change in current. And dt is the time interval in which this happens. So that's all about self-inductance. Now, what is the unit of self-inductance? Self-inductance has a unit, SI unit, Henry, having a symbol H. Do you remember Henry? We saw in the first lesson of this chapter that along with Michael Faraday, Henry and Lenz also conducted the similar experiments and came up with similar results but in different parts of the world. Michael Faraday from UK, Henry from US and Lenz from Russia. But it was Michael Faraday who first published the results. So the credit of discovering electromagnetic induction goes to Michael Faraday. But we cannot forget the contributions made by Henry and Lenz in the field. So in order to honor Henry, we have kept the SI unit of self-inductance as Henry. And 1 Henry is equal to 1 Weber per ampere. Can you guess from where I got this? Here, phi is equal to Li. So L is equal to phi by I. Remember, the unit of phi is Weber and the unit of I is ampere. So 1 Henry is equal to 1 Weber per ampere. Also, 1 Henry is equal to 1 volt per ampere per second. From where did I get this expression? Yes, from this equation. Here you know that EMF is in volt and di by dt will be in ampere per second. So if I take this to the other side, what will happen? It will be 1 Henry and the number of turns doesn't have any unit. So we can take only the unit of self-inductance, which is Henry. 1 Henry is equal to volt per ampere per second. So if I just rearrange this, so per second, when it goes to the numerator, will become second and ampere will become ampere inverse. So 1 Henry is also equal to 1 volt second per ampere. So I hope self-inductance is clear to you. If you have any doubts regarding this, please give me in the comment below. Now, let us see what is meant by mutual inductance. Or before that, I would like to discuss with you a special concept called non-inductive coil. Now, sometimes self-induction is not desirable. Why? It opposes the main current of the circuit. Suppose we need in a circuit a 4 ampere current. Now, due to self-inductance in a coil of wire, what happens? EMF is developed opposite to the applied current, and what happens? It opposes the applied current. So a small back current is developed, say 1 ampere. So what will be the resultant current we get in the circuit? It will be 4 ampere minus 1 ampere because 1 ampere is in a direction opposite to this 4 ampere. So self-induction is sometimes not desirable. Therefore, in order to minimize the effect of self-induction, The coil is made in a special manner called non-inductive coil. Here, this is made of a single coil of wire. And in order to make the magnetic flux more stronger, we may even keep an iron core in between. So here this is an example for usual coil, which is inductive, which means it has self-induction if connected to an external circuit. Now, in order to develop a non-inductive coil, which means a coil of wire in which there is no self-induction, you have to first make a two-fold of the same coil of wire. Let me come back when you read this with a coil of wire so that I can show you. What I have here is the wire of a Okay, so first of all, let us consider this is a coil of wire. Then we have to make a two-fold of it like this. And then wound this two-fold on a bobbin. So I'm going to wind this two-fold on a pen like this. Okay, so here what I get is double wires. As you can see here, it will end here. Okay, so instead of using a single coil of wire, straight away wound, we are using a coil of wire which is first wound into a two-fold and then it is wound or curled onto a bobbin. Bobbin means anything like a pen, where if the wires are very strong, once I remove this pen, its shape should remain like this as shown in this third figure. So this is the shape. So what happens now? If I apply current through this end, I will get back the current through this end. Okay, so let me show the figure to you. Here, if we apply current here, it will go through this wire like this, through all the turns, and it will get back, and now it's going in the opposite direction and comes back through this terminal. Now here, in one half of this coil of wire, the current is flowing in one direction. And in the other half, the current is going in the opposite direction. There's two adjacent wires. Here you can see two adjacent wires carry current in opposite direction. Here current is going in this direction. While the nearby wire, you can see it is in the opposite direction. So the EMF induced by this current will be in one direction and the EMF induced by this neighboring wire will be in the opposite direction. So what happens? They cancel each other. So the self-induction produced by the wire which carries current in this direction will be cancelled by the EMF self-induction produced by current flowing in the adjacent wire where the current is flowing in the opposite direction, because they will be in opposite direction. So when you wind the coil of wire in this manner, which is usually called the non-inductive coil, we can minimize self-induction. So in certain situation where self-induction will result in a loss of current required, we usually wind the coil in this manner. I hope this is clear to you. And if you have any doubts, you can give that in the comment below. Now let us see the next concept called mutual induction. So mutual induction means there should be two coils of wire. Self-induction, there is only one coil of wire. the change in current in that coil of wire itself will produce a EMF opposing the same current that produced it. Now, in mutual induction, as you can see here, there should be two coils of wire placed near to each other. One of the coil is connected to a source, a voltage source, here shown as plus minus. So this is usually called the primary, where we apply a voltage. This is called the primary, or I will call it the first one. So here, the first coil of wire, we are applying a voltage. Now, another coil of wire, which is usually called the secondary, is kept near to it. It does not have a source of voltage. It has a load, means any resistance, any device. And here you can see a galvanometer that indicates the presence of current in the coil. Remember, this coil of wire doesn't have any source of voltage. It is not connected to a cell or a battery. This one is connected to a source, voltage source like a battery. So let us see what happens when the current increases. Now, when we switch on, what happens? The current will slowly increase. As the current increases, what happens? A magnetic flux is developed within the coil. And just as we saw in self-induction, as the current increases, the magnetic flux also increases. Now, there will be self-induction in this primary coil, no doubt about it. But there is a nearby coil. So there was no magnetic flux linked with the coil in the beginning. The magnetic flux was 0 Weber. Now, when the magnetic flux in the nearby coil changes, what happens? The magnetic flux that is linked with this coil of wire will also change. So initially, when the magnetic flux linked with the secondary coil was 0 Weber, it will slightly increase. Say it will increase up to maybe 3 Weber. So what happens? Magnetic flux change will result in electromagnetic induction. Just like Michael Faraday's law of electromagnetic induction, there will be a self-induction in this coil, and at the same time, there will be a mutual induction in this secondary coil because it is kept near to this coil. It is kept near to the primary. So when a current flows in the primary coil, there is a change in the magnetic flux linked with the secondary coil, and this will result in an EMF developed in the secondary coil. So this is what is happening when we switch on current in the primary coil. So from this, let us see how is mutual induction defined, or what is meant by mutual induction. If, due to change of current in a coil, electromagnetic induction is produced in another nearby closed coil, then that induction is called mutual induction. So for mutual induction, there should be two coils of wire. We are applying some current in one coil of wire, which we call the primary. As a result, the magnetic flux linked with it changes, and if there is another coil near to it, the magnetic flux linked with it also will change, resulting in the induction or electromagnetic induction in the secondary coil. So this is called mutual induction. Now, you may have a doubt if self-induction happens in the primary coil. Yes, it will be there. And in addition, there will be mutual induction in the secondary coil. So let us mathematically see this situation. If phi is the magnetic flux developed in the second coil, which is called the secondary, due to the current I in the first coil, that is primary. So we know that more current, more will be the magnetic flux induced in the first coil, and more will be the magnetic flux transferred to the second coil. So, the magnetic flux developed in the second coil is directly proportional to the current in the first coil. So, phi is directly proportional to I, where phi is the magnetic flux developed in the secondary coil and I is the current in the primary coil. Or you can say that phi is equal to a constant of proportionality M into I. And this constant of proportionality is called mutual inductance. So mutual inductance is represented by the letter M. Remember, what is the letter that represents self-inductance? It is L, and it will have a different value from M. So phi is equal to Mi, where M is called mutual inductance or coefficient of mutual induction. Here we will call it mutual inductance. Now again, in the similar way we defined L, self-inductance, we can define mutual inductance. So if I is equal to 1 ampere, M will be equal to 5. So if I is 1, M will be equal to 5. And from that, we can define mutual inductance as the magnetic flux linked with the secondary coil when unit current flows through the primary coil. Okay, so the definition is similar, but you have to mention here secondary coil and primary coil appropriately when you define mutual inductance. So mutual inductance is the magnetic flux linked with the secondary coil when unit current flows through the primary coil. We got this definition from this equation. Now, you know Michael Faraday's second law of electromagnetic induction, which says that the EMF developed is directly proportional to the rate of change of magnetic flux. So let us apply that in this case. So E or epsilon is the EMF induced in the secondary coil due to the change in this flux, magnetic flux phi. Then EMF is equal to minus d phi by dt. Here EMF E is the EMF developed in the secondary coil and phi is the flux, magnetic flux developed in the secondary coil. But we know that the magnetic flux phi developed in the secondary coil is equal to Mi from this equation. So EMF E is equal to minus dMi by dt. Again, M, the value is a constant which does not vary with time. Only the current is increasing, only current changes with time. So we can take M as a constant out of this differentiation and we will get EMF E is equal to minus M di by dt. So what is di by dt? Di by dt is the rate of change of current in the primary coil because flux is produced in the secondary coil due to the change of current in the primary coil. So EMF produced in the secondary coil is equal to minus M into di by dt. So from this, we can get another definition for mutual inductance. If di by dt is equal to 1, then M will be equal to E, its magnitude. So mutual inductance is also defined as the EMF induced in the secondary coil if the rate of change of current in the primary coil is unity. Similar to how we defined self-inductance, but in this case, you have to mention which is secondary, which is primary. So the current change is happening in the primary coil and as a result, EMF is induced in the secondary coil. And this process is called mutual induction. I hope this is clear to you. And the unit of mutual inductance is also Henry. So it has the same unit as self-inductance and we have earlier described what is Henry. So 1 Henry is equal to 1 Weber per ampere. That's from this equation. Can you tell me what will be 1 Henry from this equation? 1 Henry will also be equal to 1 volt per ampere per second. So that's all about mutual induction, and I hope it is clear. If it's not, please ask me doubts in the comments below. Now, let us see where this mutual induction is applied. It's applied in a device called transformer. So let us see the application of mutual induction in transformer. I know that you have already learned about transformer in your grade 10. Now this will be a revision of the topic and also a little more than that. What is a transformer? It's an instrument which changes high alternating voltage into low alternating voltage and vice versa. What is meant by vice versa? It can also change low alternating voltage into high alternating voltage. So, accordingly, transformers are of two types. One is step-up transformer. What will a step-up transformer do? It will change a low alternating voltage to a high alternating voltage. See, I'm telling here alternating voltage instead of just voltage. We will see why I have to specify here alternating voltage later in the same lesson. So step-up transformer is a transformer that can change a low voltage into a high voltage, and it should be alternating voltage. Now, step-down transformer is a device that can convert a high voltage into a low voltage. Now, let us see what are the parts of a transformer. Here you can see the picture of a transformer, a diagram of a transformer. It is made of two coils of wires. See, these are the two coils of wires shown in red color and in blue color. It contains two coils of wires wound at the opposite sides of a soft iron core. So this is a soft iron core, and these two wires are wound at its opposite ends. And the coil where an alternating voltage is applied is called primary. So here we give an alternating voltage. We give a voltage. This symbol is shown for alternating voltage, changing voltage. So here we apply a changing voltage represented by EP. So this is called the primary coil. We are applying a voltage called EP to the primary coil, and a current IP flows through this primary coil. Suppose the number of turns in this coil is NP. So this is the primary where we apply the voltage. Now the coil where alternating voltage is applied is called the primary, while the coil where alternating voltage is induced or produced is called the secondary. As we saw in mutual inductance, when we apply current to a primary coil, what happens? In a nearby secondary coil, a EMF is induced. So if you are applying a alternating current or alternating voltage in the primary, you will get back a alternating EMF or alternating current in the secondary coil by mutual induction. So here, when we apply EP current, EP voltage in the primary, you will get ES voltage induced in the secondary. And if the current in the primary is IP, we will get an induced current IS in the secondary. And if NP is the number of turns in the primary, let us express NS as the number of turns in the secondary. Now note here, the number of turns are different. which has more number of turns? From the figure, primary has more number of turns. Okay, later, looking at these number of turns, you will be able to identify whether this is a step-up transformer or a step-down transformer. Wait a little more until we discuss more. So here, let me express to the primary coil Michael Faraday's law of electromagnetic induction, according to which the EMF is directly proportional to the rate of change of magnetic flux. So we can say that EP is equal to minus NP into d phi by dt. So NP is the number of turns in the primary and phi is the magnetic flux produced in the primary, and T dt is the small time interval in which it is produced. See, if all this flux which is produced in the primary coil is carried to the secondary, that's why we are winding that around a iron core, a soft iron core. You know that a soft iron material is magnetic. So if you apply a magnetic field at one end of this iron, you know that it will become a magnet. It will become a magnet, and that magnetic field will be there throughout the material. So when we use a soft iron core, the magnetic flux produced in one end will be carried to the other end without much loss. So we assume that all the magnetic flux which is produced at the primary reaches the secondary. So we can write the same equation at secondary. Es is equal to minus ns d phi by dt. We assume here that all the flux produced in primary reaches the secondary. So we got these two equations. Now let us divide these two equations. So EP by ES will be equal to negative and negative sign gets cancelled. D phi by dt gets cancelled. So what remains is NP by NS. Therefore, we get the equation EP by ES is equal to NP by NS by dividing these two equations. So here we see that the number of turns in primary is directly proportional to the EMF in primary, and the number of turns in the secondary should be directly proportional to the number of EMF in the secondary. So in a step-up transformer, it changes a low voltage to high voltage. So we give a low voltage in the primary and we get back a high voltage in the secondary. So here EP is low if it was a step-up transformer, and the number of turns should be less. Is it like that in this figure? No. Now let us see step down transformer. A high voltage is changed to low voltage. So we give in the primary a high voltage and we get back in the secondary a low voltage. So the voltage in the primary should be more. So the number of turns in the primary should be more. So can you guess what kind of transformer this is? Is it a step up or a step down? It's a step down transformer because here EP will be more because NP is more. And here ES will be less than EP because NS is less than NP. So here we get we apply a high voltage and we get back a low voltage, which means this is a step down transformer. Now, again, let us assume that there is no loss of power or energy. So when we use a soft iron core, as I told before, all the magnetic flux produced in the primary get transferred to the secondary. So we assume that there is no dissipation of energy in this core. But that's a little bit of ideal case. We know that Whenever current is flowing, some amount of heat will be produced and some energy will be lost. That's the actual case. But here, we assume the ideal case where there is no power loss or no energy loss. So the input power, the power that we give in the primary, we obtain it in the complete form in the secondary. So input power in the primary will be equal to the output power that is in the secondary. What is power? How will we express electrical power? We have learned that power is equal to V into I. V is the voltage, I is the current. So here we are expressing voltage by the letter E. So power in the primary is equal to EP times IP, voltage times current in the primary. And power in the secondary is equal to voltage times current in the secondary. So ES into IS. Now, if we take IS to this side, or sorry, ES to this side, it will become EP by ES. And if I take IP to this side, it will become IS by IP. Therefore, from this equation, we get that EP is inversely proportional to IP and ES is inversely proportional to IS. So, if there is more voltage in the primary, there will be less current. And if there is less voltage in the secondary, there will be more current. So can we go back to step-up transformer, which changes low voltage to high voltage, which means it will be changing high current to low current. It's the inverse for current. Now, step-down transformer will change high voltage to low voltage, which means it will be changing low current to high current. Okay, so we have combined these two equations and together written it as EP by ES is equal to NP by NS and is equal to IS by IP. So the current is in the reverse form as from the voltage and the number of turns. So using this equation, if you know any three of these quantities, you can get or you can mathematically find out the other three quantities. So only if you know the three quantities in this, you will get all the six quantities represented in this equation. So that's about transformer. What is a transformer? It's an instrument that changes a high alternating voltage to a low alternating voltage and vice versa. And it is applying mutual induction, and there are two coils of wires. One is called the primary, where we give the voltage, and then another one is called the secondary, where we get back the induced voltage. And these two wires are wound on a soft iron core. And remember that more turns in the primary means more voltage in the primary and less current. And if there is less number of turns in the primary, it means there will be less voltage in the primary and more current. So let us see why I was using alternating voltage, and it should be alternating current as well. Why the transformer works only with AC, that is alternating current, and not with DC, direct current. I hope you know what is DC and AC. DC or direct current is a current that does not change with time. It remains in a constant value. So when we switch on, the current changes from 0 to say 3 ampere. And and then its value will be 3 ampere itself throughout. There is no change. While in AC, if it's a 3 ampere AC current, the current will change from 0 ampere to 3 ampere, then it goes back to 0, then in the reverse direction 0 to minus 3 ampere, then it goes back to 0. It keeps on changing. It will change several times in a second. The supply current which we receive at homes, they are AC in nature. They change around 50 times in a second. So it keeps on changing. Now remember Faraday's first law. Electromagnetic induction is induced, or electromagnetic induction happens only if there is change in magnetic flux. EMF or current is induced in a coil of wire due to a change in magnetic flux. And this induced EMF or current will exist only as long as the magnetic flux changes. So if we apply a DC, momentarily it will change in the beginning. Then it will be constant. It's not changing. So current will not be induced. So the induced current will be there in the secondary only for a fraction of a second, and then it will not be there. But if you are using AC, it will be always there because it keeps on changing. And this change in magnetic flux is required to keep induced current. So if you are giving a AC, we will continuously get a induced current in the secondary. So the working principle of transformer depends on Faraday's law of electromagnetic induction. When AC flows through a primary coil wrapped around a soft iron core, it generates a changing magnetic field. This makes an alternating voltage in the secondary coil. If DC was applied, there would be no change in the magnetic flux and therefore no flow of current in the secondary coil. So that is why transformers work only with AC, not with DC. Now, let us again analyze the case of step-up and step-down transformers in the light of this equation. So, step-up transformer and step-down transformer. Step-up, as we saw before, converts low voltage to high voltage, and step-down converts high voltage to low voltage. And from here we know that voltage and current are in inverse relation. So step-up transformer converts a high alternating current to low alternating current, and a step-down transformer converts a low alternating current to a high alternating current. Just the reverse of voltage. And since a step-up transformer converts low voltage to high voltage, its voltage in the primary will be less than the voltage in the secondary, because in the primary we are giving a low voltage and in the secondary we are receiving a high voltage. So the same relation applies for the number of turns. More voltage in primary means more voltage in the more number of turns in the primary, and so less voltage in the primary means less number of turns in the primary, and high voltage in the secondary means large number of turns in the secondary. So NP is less than NS, and the reverse for current. So IP, current in the primary, will be more than the current in the secondary, high current to low current. So in a step-down transformer, it's just the opposite. IP is greater than IS, NP is greater than NS, and IP is less than IS. You can analyze that in the light of these two statements and also this equation. Now, where we use a step-up transformer and where we use a step-down transformer. Usually, when current or voltage is developed in a power generating station, it should be transferred through large distance before it is distributed to different homes, factories, etc. So this current will travel through wires for a large distance. We have learned in current electricity chapter in the beginning that if current flows through a coil of wire, what happens? It produces heat, Joule's heating effect. And how much heat was produced? H is equal to I square RT, where I is the current, R is the resistance of the coil of wire, T is the time taken. So if current flows through the wire for a long time, through long distance, more heat will be lost if it has a high value of current, because heat produced is proportional to I square. So more current means large amount of heat will be lost. So if you are sending a high amount of current through large distance, what happens? The current, if it is high, a lot of energy, electrical energy will be lost as heat. Now we don't want this electrical energy to lose. So what we do? We will reduce the amount of current before it is transmitted through large distances. So there is an inverse relation between current and voltage here. So we want to reduce the amount of current, which means we will increase the amount of voltage. So low to high voltage. Then what happens? The current will become low. So we use a step-up transformer near power generators before transmission of current through long distances, so that the current that is transmitted through long distances will have a low value for current, and hence a lesser amount of heat will be lost during this transmission. Now, when we get back the current, we don't need this high voltage current in our homes. We need to reduce the voltage. So what should we do? We should use a step down transformer. So once we bring the current which is generated at the power generating stations to the place where it is distributed to homes, we will use a step down transformer. So step down transformer is used to reduce this high voltage which is coming. That is the low current which is coming to a high current. And it is used near transmission line before supply of current to individual homes. And here you can see the picture of different transformers. Here, this is a small transformer which are used in laboratories and all. So I have worked with this transformer. It's very small transformer, very handy, which we can use in the laboratory while doing experiments, because the supply voltage is around 220 volts. But if we are connecting something to a circuit, we may be requiring only 6 volts, 9 volts, like that. So we have to step down. So this is what is used in a laboratory. And here, this is a transformer which is used near the transmission line. These are the transmission lines before supply of current to individual homes. So sometimes we will not have current because the transformer broke it. So this is the transformer that does that. So this is the one. This will be a step down transformer that converts the high voltage which is coming from the power generating stations to a low voltage before it is distributed to homes. And here you can see a large transformer usually used near to a power generating stations, or maybe near to transmission lines. And so the transformers can be of different sizes and of different purposes. So that's all about transformers. So today we learned self-induction, mutual induction, and how mutual induction is applied in transformers. We saw why transformers work only with AC and not with DC. And also we saw the difference between step-up transformer and step-down transformer, and we learn few formulas. So hope you understood this concept, and if you haven't, and if you have any doubts, please let me know through the comments. Thank you for listening to the end.